Good morning, everybody. We made it. Okay, let's get started. Okay, so today we're going to really pick up where we left off from yesterday. We're going to learn about the second derivative test, and then if we have time, at the very end, I'll show you how it can be used, how everything we've used so far can be used for sketching your own pretty accurate curves of some function that you might be interested in. Okay, so announcements. You got homework due Monday and exam one in a week. I'm going to post a review over the weekend. I currently have it up on my computer right now, working on it. Okay, so make sure you study for the exam. And also, uh, as everybody's coming in, as an experiment that I'm doing for another class, can everybody please in the chat put in your birthday, just day and month? I don't need the year, but birthday, day and month. Okay. So let that roll in. Thank you guys so much. Birthday, birthday. Okay. Cool beans. All right. So, any questions about the review, about the exam, about homework, about anything? Okay. So, last time we stopped here, we wanted to find points of inflection for the function f of x is x to the fourth plus x. Okay, so really quick, let's remind ourselves what a point of inflection is. So a point of inflection, it's not just where f double prime of x equals 0. This is not just what a point of inflection is. Okay, a point of inflection is where f double prime of x changes sign. Or in other words, where f goes from concave up to concave down, or concave down to concave up. Okay, so for this example here, we're looking at f of x is x to the fourth plus x. So to find points of inflection, what do I need to find first?
First derivative.
Yeah, I should find the first derivative, and then that'll help me find the second derivative, right? So what is f prime of x here? Well, what's the derivative of x to the fourth with respect to x?
4x cubed.
4x cubed, good. And then what's the derivative of x with respect to x?
1.
Plus a 1, very good. All right, and so f double prime of x is equal to what?
12x squared.
12x squared, excellent. So then where does this, although points of inflection aren't just where f double prime equals 0, you should, if you're looking for points of inflection, solve for where this equals 0 so you can evaluate where it changes sign, if it does at all. Okay, so where does 12x squared equal 0? For what x? Yes, thank you, Saba. X equals 0. Okay, so I need to evaluate the sign of this. 12x squared. This is defined from minus infinity to infinity. So those are going to be my endpoints. And then I'm using, I got at x equals 0, this thing is 0. So what test value should I use on either side of this? Oh, I don't want to give it away. I gave it away. Oh no. What test value should I use on the left?
-1.
Yeah, -1. So what do we get for 12x squared when we plug in x equals -1? Is it positive or negative?
Positive.
Positive. And what about on the other side? When we use x equals 1?
Positive.
Also positive, right? And we really didn't even need to even plug anything in. It's 12 times x squared. X squared doesn't change signs, right? So this is concave up everywhere but x equals 0. So are there any points of inflection for this function?
No.
No, there are no points of inflection. No points of inflection. Okay, so even though we got a point where the derivative or the second derivative of f is 0, we don't get that that's a point of inflection because f double prime doesn't change signs there. Okay. Any questions for that? Is there a way we can memorize signs for up and down? Yes, I'm going to show you. There's a cute little trick that I'm going to show you today about how to memorize when f is concave up versus concave down with you using the sign of f prime or f double prime rather. Okay, so that brings us to the second derivative test. Okay, so this is a second way to test if a function has a relative maximum or a relative minimum at some x value. Okay, so the second derivative test is going to be the following. Okay, so we're going to say f of x is a function such that f prime of c is equal to 0. So that means c is a critical number of f, right? And the second derivative of f of x exists on an open interval containing c. Okay. So if f double prime of c, f double prime at the critical number, if that is positive, then f has a relative minimum at c comma f of c. Okay, and if f double prime of c is negative, then f has a relative maximum at c f of c. Okay. And then lastly, if f double prime of c is 0, then the test doesn't tell us anything. Okay, it tells us nothing about whether f of c is a minimum or a maximum, and we need to use probably the first derivative test to tell us whether f of c is a minimum or a maximum. Okay. So let's look at a proof, at least for the relative maximum. We want to find out, so for a relative maximum, that means we're looking at the case f prime of c is equal to 0, so c is a critical number, and f double prime of c is less than 0. Less than 0. Okay. I want to use these two things to show that f has a relative maximum at c. Okay. Well, to do this, this actually doesn't rely on the mean value theorem, surprisingly. Everything we've done so far after the mean value theorem relied on the mean value theorem. But really, you just need to look at f double prime of c is equal to the limit as I'm going to use the alternate form of the definition of the derivative. Okay, so it's the limit as x approaches c of f prime of x minus f prime of c divided by x minus c. Okay, the second derivative of f at c is the derivative of the first derivative. Okay, and so here I've just written out the definition of the derivative for f prime of really c. Okay. But what is this? What is f prime of c?
0.
That's 0. Very good. 0. So really we're looking at, oh, oops, I did not give myself any room. Really, we're looking at then f double prime of c is equal to the limit as x approaches c of just f prime of x divided by x minus c. Well, let's look for a second. We also know that this, we're assuming, is less than 0, right? This is strictly less than 0. Okay, so because of this, if we take x bigger than c, and we're looking at f prime of x over x minus c, well, for x close enough to c, that's what this limit means. For x close enough to c, this thing has to be negative, right? If f double prime of c is negative, then when x gets close enough to c, the stuff inside the limit also has to be negative. But then if x is bigger than c, what sign does x minus c have?
Positive.
It's positive, right? So that means I have something divided by a positive gives me a negative. So that means if x is greater than c, that tells me that f prime of x has to be less than 0. It has to be negative. Okay. Well, let's look at it from the other way. Let's say x is smaller than c. Well, again, as long as x is close enough to c, then this still has to be negative because, again, in the limit, f double prime of c is negative. So that means this thing, when x is close enough to c, this guy has to also be negative. Okay. But now, if x is less than c, what sign does this have? Yeah, if x is less than c, then I can say, if I subtract c from both sides, then x minus c is less than 0, right? So what sign does x minus c have?
Negative.
It's a negative, right? So I get something divided by a negative gives me a negative. So that means if x is less than c, then f prime of x has to be positive. So then we can make a little table with c in the middle. And for all of this, I've said x is close enough to c. So really, I don't know what's going to go here. I'm just going to call it a and b. But really, all I'm trying to get across is that we're close enough to c on the left and right. Well, then, if x is less than c, we just showed as long as x is close enough to c, we just showed that f prime is positive, right? Positive. So that f has to be increasing on the left of C. Okay. We also showed that if X is bigger than C, then F prime is negative. And so by the first derivative test, we get that F has relative maximum at C F of C. Okay. So the proof of this really just used the definition of what the derivative is, but we really applied it to the second derivative, or we applied the definition of the derivative to the first derivative to get the second derivative. And then from there, we just used the first derivative test to kind of prove the second derivative test. Okay. So, and if you try to show that F has a relative minimum, if F double prime is positive, then the proof goes exactly the same way. Okay. So the dumb little trick that I use to remember which sign gives me a positive versus which sign gives me a negative is this. If we're looking at F prime of C is equal to 0, then if the second derivative is positive, then we have a relative minimum at C. Okay. If the second derivative is negative, we have a relative maximum. Okay. This is the dumb little trick, a smiley face and a frowny face, that I use to remember which sign gives me a maximum versus a minimum. And it also helps you remember if the second derivative is positive at a point, that means f of x is concave up, right? So you can use that, that trick also to remember that a positive second derivative gives you a concave up function. Okay. So are there any questions about the second derivative test? How it's used? All right. So let's find and classify using the second derivative test. The relative extrema of the function f of x is -3 times x to the 5th plus 5 times x to the 3rd. Okay, what do I want to do here?
Take the derivative.
Yeah, I need to take a derivative, right? Now I'm finding relative extrema. So I'm going to take the derivative and do what with it? Yeah, I'm going to take the derivative and I'm going to set it equal to 0, right? So what is f prime of x? Well, what do I get from -3x to the 5th?
Negative 15x to the 4th.
Perfect, -15x to the 4th. And then what do I get from 5x to the 3rd?
15x squared.
Plus 15x squared, right? Or in other words, both of these have a 15x squared in them, 15x squared times, well, I will be left with, when I pull out 15x squared from there, I'm going to be left with -x squared plus 1. Okay. So I want to solve 15 times x squared times, I'm going to rewrite this as 1 minus x squared. I want to solve this is equal to 0, right? So what do we get? We get x equals what for this?
We should get x equals 0 and then x equals plus or minus 1.
Good. From this first factor, we get, when we set x squared equal to 0, we just get x is 0, right? And then from this factor, when we set 1 minus x squared equal to 0, I'm going to get x is equal to plus or minus 1. Okay. So I've got 3 critical numbers that I need to check. So I'm going to try to classify these using the second derivative test. So in order to use the second derivative test, I probably need to find the second derivative, right? So f double prime of x is equal to what? I would differentiate this form. So what's the derivative of negative 15 times x to the 4th?
Negative 60 x cubed.
Negative 60 times x cubed. Good. And then what's the derivative of 15x squared?
30x.
30x plus 30x. Very good. All right. So I need to check f double prime of negative 1, f double prime of 0, and f double prime of 1. And I really only need to check them for their signs. Okay. So when I plug in negative 1 into f double prime, what do I get? Yeah, I'm going to get, when I plug it in
Negative.
here. Oh, go for it.
A negative.
Yeah. Oh, careful. I think I'm going to get negative 60 times negative 1 plus 30 times negative 1. But this will be a positive, right? So I should get 60 minus 30 is plus 30, which is positive, right? And then f double prime of 0, what do we get?
0.
Just 0. Good. And when I plug in x equals positive 1, then I'm going to get a negative, right? I'm going to get negative 60 plus 30 gives me negative 30, which is less than 0. So remember, second derivative positive gives me a relative minimum. If the second derivative is negative, I get a relative maximum. So that means that f of negative 1 is a relative what? At negative 1, we got a positive second derivative. So that means f of negative 1 is a what?
Relative minimum.
Relative minimum. Very good. Okay. And similarly, at one f of 1, we have a relative what? Well, f double prime of 1 was negative. So my
Relative max.
yeah, that's a relative maximum. And then what does the second derivative tell us about c equals 0? Yeah, no, go for it.
Nothing.
Yeah, the second derivative test fails for c equals 0. So I need to do a little bit more work. Oops. I need to do a little bit more work to find out what's happening at 0. Okay, so in order to do that, we need to fall back on the first derivative test to check and see what's happening for x equals 0. So let's do that. So my first derivative test, well, negative infinity. We could include x equals plus and minus 1 in this chart, but we already know what's happening at x equals plus and minus 1. So instead, I'm just going to put 0 up here. Okay, so f prime of x was equal to 15x squared times 1 minus x squared. So 15x squared times 1 minus x squared. Okay, so f prime of x was the product here. All right, well, the first row here, what should I fill in this chart?
Positives, since it's a quadratic.
Positive, yeah. Positive, positive. The second row, 1 minus x squared. And remember that x is close. Really, x is between, I can even do this because we really only care about this between -1 and 1, right? So what sign does 1 minus x squared have between x equals -1 and x equals 0? It's positive, right? You could choose x equals 1/2, for instance. You get 1 minus 1/4. That's positive. What about to the minus 1/2? What about to the right of 0? Well, again, I could choose x equals positive 1/2, and I get also a positive, right? So f double prime of x is positive here, positive here. So that means f of x just sort of levels out. There's no relative min or maximum at x equals 0. Okay. So that means, so taking this all together, f of -1, we know that f of -1 is a relative minimum, right? So f of -1, well, what is that? That's going to be -3 times -1 gives me +3, and then -5 is -2, right? So f of -1 equals -2 is a relative minimum. And then similarly, f of +1 is equal to -3 plus 5 is +2 is a relative maximum. Okay. Questions on that? All right. Let's find and classify the relative extrema of f of x is equal to 4 over 1 plus x squared. Okay, so what should I do here if I'm finding relative extrema? I need f prime of x, right? So how do I find f prime of x here?
The quotient rule?
Quotient rule sounds good to me. So with quotient rule, I'm going to do low d high. Well, d high here is just 0, right? So really, I just need high minus high d low. So what's the derivative of low?
Just 2x.
Just 2x over the square of what's below. And yes, I have the question. Could we just write this as 4 times 1 plus x squared to the -1 and use the chain rule? And the answer is yes, absolutely. We could do that and not use the chain rule. Or sorry, not use the quotient rule. Either way. Which is better? It's just a preference thing. I would personally do this, but I've done a million of these problems, so it's really just a personal preference thing. Okay, so this is equal to -8 over 1 plus x squared. All right, what do I want to do with this?
Set it equal to 0.
I want to set it equal to 0. Very good. And so where does this equal 0?
Zero.
Yeah, exactly. If a fraction equals 0, that means that the top is equal to 0. So that means x has to be 0. If -8x is 0, then x is 0. Very good. All right, and notice I didn't ask you to use a specific test. So which test would you guys rather use? First derivative test or the second derivative test?
Oh, the first one.
Yeah, that's we can do the first derivative test here. That sounds reasonable to me. I'm going to let you in on a secret. I much prefer the first derivative test. If you'd rather do the second derivative test on this one, that's fine. But you're going to need to take the derivative of that quotient. And within the quotient rule, you're going to need to use the chain rule. And then you're going to need to plug in x equals 0 after that. I'd rather just examine the sign of -8x and so on. Okay, so this function is defined from -infinity to infinity, and we have one critical number that we're testing out here, right? So this function is made up of -8x and 1 plus x squared. So what does the bottom row look like?
Positive across the
Yeah.
board.
Positive across the board. Very good. What does the top row look like? Well, I could plug in x equals what for this first entry?
-1.
Yeah, I could plug in x equals -1. So what do I get from this when x is -1? Positive or negative?
Positive.
Positive. Very good. And what do I get when x is, say, +1?
Negative.
Negative. Very good. So f prime has to look like positive, negative. So what kind of relative extreme value do we have at x equals 0?
A relative maximum.
A relative maximum, because f prime goes from positive to negative. So that means f looks like increasing to decreasing. We have a relative maximum. Okay. So let me add a page. Add page. So that means that f of 0, which is 4 over 1 plus 0, so 4 equals 4, is a relative maximum. Okay. Do we have any questions on that? All right, so this always brings up the question, which test is better, right? Which one should I use more often? Oh, that's a good question. Someone asked, could we say it's an absolute maximum? And the answer is that yes, this has an absolute maximum at x equals 0. This test doesn't show that it's an absolute maximum. You need to use slightly different arguments to show that it's an absolute maximum. Okay. All right. So the question is, which test is better? Which one's better for showing that a relative extreme value is a relative minimum or a relative maximum? And the answer is it depends on the particular problem. Okay, sometimes it's going to be easier to quickly take some functions. It's very easy to take 2 derivatives. If you just have a polynomial, taking 2 derivatives is very quick, and plugging in critical numbers then is probably going to be the easier way to go over, say, looking at the sign of f prime. If f prime factors into a really big mess of products, then it might be really messy analyzing the sign of f prime, whereas just plugging a number into f double prime might be very simple. Okay, so sometimes this is hard. You're usually going to use the second derivative test when that's the case. Other times, looking at the sign of f prime might be really easy. We've seen several cases of that. Okay, the one thing that I think gives the first derivative test a pretty big edge over the second derivative test is that the first derivative test works in more situations. Okay, we saw a situation. I showed you a situation where the second derivative test told us nothing about a critical number, where the first derivative test told us that the critical number gave us neither a minimum or a maximum. Okay, and the second derivative test, if you're looking at a really simple function like f of x is equal to x to the 4th, well, this function just looks mostly like a flattened parabola. It has a relative minimum at x equals 0. But if you take a derivative, you're going to get 4x cubed. And then when you take a second derivative, you get 12x squared. And so this tells me that I have a critical number at x equals 0, but f double prime of 0 is 0. And so even in this simple case, the second derivative test fails to tell us anything very interesting, even though it's very easy to see that there's a relative minimum at x equals 0. Okay, the first derivative test doesn't fail in this situation. So for that reason, I personally most of the time will prefer to use the first derivative test. But you do need to know how to do both tests. There are some questions I might give you where there's no way around it. The second derivative test is the only way to do the problem. Okay, so you do need to know both. It's okay to have a favorite, but you do need to know both. It's just like having children. No, that's a joke. Don't have a favorite child. Okay, any questions about any of this? Okay, so let's find and classify all the relative extrema for the function f of x is equal to x squared minus 2x minus 7 times e to the x. Okay, so yes, let's look at, to find relative extrema, very first thing you're always going to do is what? Yes, take a derivative. Thank you, Safa. So f prime of x is equal to, well, how do I take the derivative of x squared minus 2x minus 7 times e to the x?
Product rule.
Product rule, very good. So product rule says take the derivative of the first function. It's going to give me 2x minus 2, and I'll leave the second function alone. And then plus, I'll leave the first function alone, and I'll take the derivative of the second function. And what's the derivative of e to the x?
E to the x.
e to the x. Very good. So when both of these terms have an e to the x in common, I'm going to pull that out in front. And then when I do, I'm going to be left with x squared minus 2x minus 7, and then plus a 2x minus 2. So notice that minus 2x cancels with plus 2x, and I'm left with e to the x times x squared minus 9. Okay, what do I want to do with that?
Can
Set it
factor it
equal to
out.
0.
Yeah, I want to set this equal to 0, right? And I'm going to factor that. There's a train coming. So 1 second. Okay, so I'm going to set this equal to 0. If this is equal to 0, then either e to the x is 0 or x squared minus 9 is 0, right? So where is e to the x equal to 0?
Never.
It's never equal to 0. It was a trick. I tricked you, but I didn't trick anybody. Okay, very good. And then where is x squared minus 9 equal to 0?
Plus or minus 3.
Yes, that means x is equal to plus or minus 3. All right, so you guys tell me, do we want to just do the first derivative test, or do you want to take a second derivative test? Let's do the second derivative test, because it's a lesson about second derivative tests. So f double prime of x equals, well, I'm taking a derivative of e to the x times x squared minus 9. So I'll take the derivative of e to the x. Oops. I'll get e to the x, and then I'll leave x squared minus 9 alone. Plus, and then I'll leave e to the x alone, and I'll take the derivative of x squared minus 9. So what's the derivative of x squared minus 9?
2x.
2x, very good. So when I factor out an e to the x again, I'm going to get e to the x times x squared plus 2x minus 9. Okay. So then I want to check, what is f double prime of negative 3? Or really, what sign does it have? Well, e to the minus 3 is positive. If I plug in minus 3 into here, well, I'm going to get 9 minus 9 is going to give me 0, and then minus 6, right? So it should give me positive times negative is going to give me a negative, really negative 6 e to the minus 3. But that should be negative, yes? And then f double prime of positive 3, well, again, I'm going to get, when I plug in positive 3 into this piece, I'm going to get 3 squared, and then minus the 9 is going to give me a 0, plus 2 times 3. So that's going to give me positive 6 times e to the 3, which is greater than 0. So when f double prime is negative, we know we get a relative maximum. When f double prime is positive, we know we get a relative minimum. Okay. So that means f of negative 3, which is equal to e to the minus 3 times 9 minus 7 plus 6. 9 minus 7 plus 6. Yeah, 9 really plus 6 minus 7. Well, that's equal to 8e to the minus 3 is a relative max. And f of positive 3, which is equal to e to the positive 3 times 9 minus 6 minus 7, which is equal to what? 2 minus 6 is minus 4. E to the 3 is a relative minimum. Okay. Any questions on that?
I have a question.
Yeah.
At the top of the page, when you have f double prime x and you have two e to the x's,
Mm-hmm.
how did you like just condense that into one right there, or cancel
Yeah,
one
yeah.
out?
Yeah, we just factor out the e to the x. Both of these have an e to the x in common. And so when I factor that out, well, I'm going to be left with x squared minus 9 from when I factor it out from there. So that's the x squared minus 9. And then a plus 2x. So I just wrote it in standard form inside that. But yeah, that was just factoring out the e to the x.
Okay, thank you.
Yeah, no problem. Any other questions? All right. So let's look at this very last problem. Look at all these things I'm asking you to do. But now that you know how to find really most of the important features of what a function is doing on any open interval, you can actually come up with some pretty accurate sketches of graphs. So let's start in on this problem. I'll finish it after class before I upload the notes. But let's start in on this problem to try and come up with a sketch of f of x is x cubed minus x. Okay, so part one, what's the domain of the function f of x here? What numbers can I plug in?
All of them? I don't
I
think
can plug
there's.
in, yeah, I can plug in all of them, right? So the domain of f of x is negative infinity to infinity. Very good. All right, so next we want to find x and y intercepts. Okay, so to find the x-intercepts, how do I do that? Yeah, to find the x-intercepts, well, that's if I get a graph going. The x-intercepts are going to be where the graph crosses the x-axis, right? So that's where y is 0. So I want to solve x cubed minus x equals 0 to find the x-intercepts. Well, I can factor an x out of there to get x squared minus 1 equals 0. So where are the x-intercepts?
At 0 and plus and minus 1.
Perfect. 0, and then I'll come over 2 to plot this point here at 1, and then over here is minus 1. Very good. There are the x-intercepts, and we found the y-intercept by chance, right? The y-intercept is also at 0, 0. Okay, so we've got the x and y intercepts. Now, critical numbers. How do I find the critical numbers of f of x equals x cubed minus x?
Take the derivative and set it equal to 0.
Good. F prime of x, which is equal to 3x squared minus 1. I want to set this equal to 0. So that tells me, well, I'll add 1 to both sides. I get 3x squared equals positive 1. So x squared is equal to 1 over 3. So x is equal to 1 over the square root of 3, positive or negative, right? So Then I found my critical numbers. So then I need to find all intervals on which f is increasing or decreasing. So how do I find where f is increasing or decreasing?
You can do the first derivative test, right?
Yeah, exactly. I can sort of kill two birds with one stone here just by going straight to the first derivative test, right? So I can, oh, oops, sorry. I can just make a table here. The domain is all real numbers, so I'm going to put plus and minus infinity there. And then we also have critical numbers out -1 over the square root of 3 and +1 over the square root of 3. Okay. So then f prime of x is just 3x squared minus 1. And then I'm going to pick test values of x equals -1, x equals 0, and x equals +1. So when x is -1, I'm going to get positive, right? When x is +1, or sorry, when x is 0, I'm going to get negative. And when x is +1, I get, again, x is a positive. So f is going like this. Okay. All right, and then I'm out of time. I'm gonna complete the rest of this problem so you guys can see how you can combine all this information into a decently accurate sketch of a graph of a function. Okay, so are there any questions about anything we covered today though? Any questions about the second derivative test or concavity?
On that last question, can you use Rolle's theorem to say that there are relative maximums between -1 and 0 and then 0 and 1?
You can use them. That's an excellent question. You can use them to say that there's either a relative maximum or a relative minimum between these critical points. You can't say for sure if it is a maximum or a minimum. You can't say for sure either way. You still do have to do the first derivative test. But that's an excellent observation that that Rolle's theorem guarantees either a maximum or a minimum between those. Any other questions? Well, all right. I'm going to post the review over the weekend. And so if you guys have any questions, also office hours are today from 1 to 3. So let me know if you're having any troubles with anything at all. And I will be available to help. Okay? Thank you all for being here and have a great weekend.
Thank you.